Okay, thank you. So I have a long title here. So basically what I want to introduce is feature engineering for predictive modeling with large-scale EMR. So I will introduce some of the recent works my group has been doing on feature augmentation, densification, and selection. So let me start with some background introduction and context. So today everybody talks about changing healthcare, so why do we say that? This is a famous figure to explain the reason. So basically what this figure tells us is the United States has spent much more money compared to other countries, but received not very long life expectancy. So that means that the so that means that the money you spend is not in a very right manner. So basically, we want to reduce the unnecessary healthcare cost and improve the quality of care delivery. And one important step is to basically how can we effectively utilize the available healthcare data nowadays. So what kind of healthcare data do we have? So we have a lot of different types of data. For example, we have activity and cost data, we have clinical data, we have pharmaceutical data, we also have patient behavior sentiment data. And how large are those data? So it is estimated that there is approximately 500 petabytes of healthcare data today, and this number is going to reach 25,000 in the next 7 years. So this is really a field with a huge amount of data. And how to effectively use all those data would be a key problem on basically changing the healthcare. So today I will mainly focus on introducing how to making use of those data to do predictive analytics in healthcare. So what is predictive modeling problems in healthcare? So let me give you some examples. The first is basically this hospital admission prediction. So this is a famous heritage $3 million price prediction, and the goal is to predicting the length of stay of a patient in a hospital in the next year. So with advanced technique, the healthcare providers can develop new care plans and strategies to reach a patient before emergencies occur, and thus reducing the number of unnecessary hospitalization. But why this is important? So it is estimated that the hospitalization account for more than 30% of the $2 trillion annual cost of healthcare in the United States. And around 20% of all those hospitalizations occur within 30 days of a previous discharge. So this frequent hospital readmission is usually harmful to the patient, and it is usually preventable. So Medicare, the Center for Medicare and Medicaid Services have a specific readmission reduction program where Medicare penalizes hospitals that have high rates of readmission among patients with some chronic disease like heart failure, heart attack, and pneumonia. So identifying patients at risk of readmission can guide efficient resource utilization and potentially save millions of dollars of money in healthcare. So another example is this health challenge organized by NFL, GE, and Under Armour. And what the goal is to basically building an innovative approach to identifying and preventing a brain injury. And what's more, this year the White House has unveiled this BRAIN initiative, which is a multi-party effort involving DARPA, NIH, and NSF. And the goal is to find new ways to treat, cure, and even prevent brain disorders such as Alzheimer's disease, epilepsy, and traumatic brain injury. So these are all good, examples of predictive modeling tasks in healthcare field. And last but not least, recently we also got an NIH funding with our partner Sutter Health and Geisinger. Basically, we want to perform research on early detection of heart failure. So in order to do a good predictive modeling job, so constructing effective features or generating good high quality features is in the heart. So In this talk, I'm going to introduce some of the works my group have been doing on basically, we call it feature engineering from electronic medical record. So this is the basic predictive modeling pipeline when we work with EMR. So we first extract or annotate features from structured or unstructured EMR and store them in a uniform format in the database. And then we got raw features from this, and we, through a feature engineering step, we got some high quality derived features and feed them into the predictive modeling module. And then we can get the predictive models and score and do predictions. So a typical predictive modeling setting is that we collect the features from the patient EMR from observation window and predict whether an adverse event, for example, it can be the onset of congestive heart failure in the future over a period of this prediction window. So after we collect the patient records from the observation window period, we can typically form the patient EMR as matrices, where the horizontal axis is the time and the vertical axis is the different medical features. For example, it can be diagnosis, lab test, medication, and so on and so forth. And then we somehow aggregate the features from those patient matrices into vectors. For example, a popular way would be to construct a bag of feature vectors. Basically, you can count over that time period, how many times each feature occurs and construct the feature in that way. And then we can feed those constructed patient feature vectors into the predictive modeling pipeline. So the first thing I want to introduce is this feature augmentation or generation. So there are several different ways on this line. The goal is to construct derived features from raw features to augment the feature space. One popular way is to basically how can we explore the temporal dynamics among those raw features. And there are also some other approaches. For example, in a recent paper published by Vanderbilt people, they use deep learning technologies to basically generate features from EMR. So I think that's a very good start. So in this talk, I will mainly introduce the what if we have time point-based representation for those raw features, and how can we explore temporal dynamics from that. There's also, because we don't have interval-based information, basically if you have the information on the duration of each medical features, you can use there as a famous framework called temporal abstraction. You can use that to do this feature generation for interval-based representation of temporal features. And for time point-based representation, basically we have a timestamp associated with each medical events for each patient. And then if we concatenating all the events happening to the same patient according to their happening time, then we can form the patient sequences, medical feature sequences. And the sequentiality of the events may indicate some important impending disease conditions, which might be, could be very important for predictive for prediction task. So one straightforward way to explore such temporal dynamics is what if we mine frequent patterns, meaning that we want to find a complete set of frequent event subsequences from those patient sequences. And those frequent event subsequences basically encode some the temporal ordering information of the events and can be served as features for predictions. And actually, sequential pattern mining is not a new problem in data mining and database. There are a whole lot of technologies we can leverage. Our implementation is based on an algorithm called SPAM, which is a sequential pattern mining algorithm based on bitmap representation, which is because we tested the performance of several well-known ones and find this algorithm the performance is really good in terms of speed and also the quality of the mine patterns. And basically, after we mine those patterns, when we want to evaluate the predictive power of each pattern, we construct a backup pattern representation for each sequence. So basically, you can imagine now each sequence is represented also as a vector. The values on each entry would be the frequency of that pattern appears in that sequence. And with this vector-based representation, we can investigate whether the quality or the predictive power of those patterns. And we evaluate them in the concrete task of the predicting the onset risk of a heart failure patient. So basically, in our data set, we have the EMR of patient from 2003 to 2005 from integrated care delivery network. And so that's 3 years of EMR, and we have over 1,000 heart failure cases and nearly 4,000 matched controls. And we use diagnosis, procedures, medications, and lab. And we use observation window 1 year, prediction window half year. So basically, we want to use the patient's 1 year EMR to predict after half year whether this patient is going to be diagnosed with heart failure or not. So this is averaged AUC, averaged, over 10-fold cross-validation, where I show the value of both. What if we only use bag of static features, or what if we use both the static and mined temporal pattern features? We can see by adding those temporal pattern features, the prediction performance can be greatly increased. And this is good. And when we present this result to the medical people, they are interested to investigate what are those mind patterns. So we built this system. Let me see. Called IBM Decision Flow. So basically, what we allow is we first allow the user to input some milestone events to specify the sequences he is interested to investigate. For example, in this case, we have diabetes, hypertension, and also with anemia as the outcome. And then after this, we're going to mine the patterns from those patient sequences that satisfies one with those milestone events in between. And in the bottom scatter plot, each dot is the mined pattern, and the color indicates the odds ratio of the pattern, with respect to the outcome, and the size indicates the correlation of the pattern with respect to the outcome. And one interesting thing is that because we specify several milestone events, so we can see over different period how the pattern changes. And for the 2D scatter plot, basically the vertical axis is a negative coverage, and the horizontal axis is a positive coverage. And also we can click a specific pattern to see the specific statistics. And this is a tool we developed for to facilitate the medical people to check, what are those mind patterns and what are the statistics, and to judge whether they are useful or not. So this is one of our work on this feature generation by exploring temporal dynamics. And the second work I want to introduce is this, we call this feature densification. So basically the EMR data, if we use the matrix-based representation, you can imagine it's very sparse. But is sparse good or not? It's good for computation, but here I give an example. So let's say for patient 1, he went to his PCP at time t and time t+2, and he was a heart failure patient. And at t+1, he didn't go to his PCP because he had a head injury, and he went to the emergency room. So at t+1, there is a heart failure diagnosis missing, but he had additional head injury diagnosis. But for patient 2, he pays regular visit to his PCP at t+1, and t+2. So in this case, there are two questions, right? The first one, if we still use a backup pattern representation, then that means that for patient 1 on the dimension of heart failure, he will have a value of 2, and for patient 2, he will have a value of 3. But does that mean at first that p plus 1, the patient, for patient 1, the heart failure is cured or not? Clearly not. And the second question is that if we use this backup pattern representation, a backup feature representation is patient 1 in a more severe condition compared to patient 2, clearly not. So in this case, we can see that one potential problem of traditional backup feature representation is that when you count the frequencies, you basically treat the absent entries as zeros, so which may not be appropriate. So what we want to do is we call densify is basically we want to impute those, we treat those as missing values, and we want to impute them. And in order to do that, we first assume that for all those features, there exists some feature groups, which are, where each features within each group are highly correlated, and they together can indicate some disease conditions. And we also assume that for each patient, the feature groups, the values of the feature groups evolve relatively smoothly, so we can impute according to, their happening time. And we use a matrix completion-based technology. So for each patient EMR matrix, we assume it can be factorized as a product of a feature group mapping matrix and a feature value evolution matrix. And furthermore, we also assume that because the patient population we have are usually heterogeneous, so we assume that we can, there exists some homogeneous groups among those heterogeneous patient cohort, and within each group, they basically share the same feature group. And we put everything together, come up with this optimization problem, and we use a block coordinate descent-based algorithm to solve that. And we still evaluate it on the previous task, which is predicting the onset risk of congestive heart failure. We compare with some baseline imputation method like row average, next occurrence carry backward, last occurrence carry forward, and linear interpolation of previous and next. And also, what if we impute we use matrix completion technologies to impute each patient records individually, and what about we treat them into a homogeneous cohort doing this shared-based matrix completion. And we did a preliminary performance evaluation with only diagnosis code, and we can see that a raw feature means that we still use the previous backup pattern feature representation, and we just treat those absent entries as zeros. We can see those matrix completion-based method can achieve a much higher performance. And here, CBA is basically our approach, which is class-based approach, and the number corresponds to what if we set different numbers of patient clusters, and they usually outperform those individual and shared-based approach. And the last thing I want to briefly introduce is basically we have those large feature space, and we do some sort of imputation, and usually the medical people want to know, okay, we have this long list of features, but I want to know which of them are most indicative. So that's a feature selection problem, and specifically in medical feature selection, one important thing is that because the domain knowledge is really important, we don't want to discard them. So basically, we want to, in the feature selection procedure, want to incorporate those we call knowledge-driven risk factors, which are basically the features provided by our medical advisors, and we still want accurate prediction and minimal redundancy, which are common requirements for feature selection. So we briefly revised the Lasso formulation and add two basically orthogonality terms to penalize the correlation between the data-driven features and also the correlation between the knowledge and data-driven features. And this is basically what the knowledge-driven features looks like. So basically, our medical advisor gave us a whole bunch of comorbidities for congestive heart failure, and this is basically shows that on the horizontal axis is basically how about starting from some knowledge-driven features, we gradually add the top data-driven features identified by our algorithm, what the performance would look like. We can see that by adding 50, we can see there is a big jump on the performance. And with the gradual adding of the rest of the features, the performance can still boost. And we also show what are the selected features look like. This is the top 10 features. We can see those features are different from the knowledge-driven features, and also they cover a wide range of feature types, including all 4 different types like diagnosis, medication, lab, and procedure. We asked some of our clinical partners, the heart failure expert, to validate all those features, and turns out 9 out of 10 are really relevant with heart failure. So let me conclude. So basically, I introduced some of our work on performing feature engineering with EMR and apply them to the prediction of onset risk of congestive heart failure. And I talked about 3 technologies: feature augmentation, densification, and selection. Okay, thank you.